Hello, everyone. The title of my keynote speech is Key Steps Toward the Development of a Humanoid Robot. My name is Xianin. So I did my first degree in China, and subsequently I obtained my master and the PhD degree in France. And this slide shows you some of my achievements. So in particular, this year I have published this book, which is about the new foundation of artificial intelligence. And you also know that I'm the editor-in-chief of International Journal of Humanoid Robotics. And my research interests cover basic research, applied research, and innovation. Okay, so for my basic research, the two keywords are intelligence and motion. So you will see my major focus is on robot-related research topics. And this is a prototype that we have developed almost 15 years ago. Today, I'm going to share with you the 5 key steps toward the development of a humanoid robot. So in particular, I will divide my speech into these 3 areas. Okay, the first item is to answer this question, why to develop a humanoid robot? And the second topics is about what is the definition of a humanoid robot. And lastly, the major part of this speech will be focused on how to develop a humanoid robot. Let's start with the first question, why to focus on humanoid robotics? So there are many reasons for people to focus on humanoid robotics. The reason number 1 is because humanoid robots are a better platform which enable invention and discovery in both skill-related topics and intelligence-related topics. The second reason is because humanoid robot technology enables the upgrade of existing industry, and also humanoid robot will enable the creation of a new product and a new service. Okay, so this slide shows you the pipeline from idea all the way to product and application. And third reason is because humanoid robots are better platform which facilitate learning and teaching in school, because the student or pupil will love humanoid robot very much. Then I will quickly go through the second topics of my speech, which is about the definition of a humanoid robot. So every one of you know, or you may know, okay, what will be the definition of an industrial robot, and you understand the difference between humanoid robot and industrial robot. Okay, so this slide basically shows you, okay, the key component inside the definition of a humanoid robot. So, and here you will see, first of all, humanoid robot is a machine which could perform a motion, and secondly, humanoid robot is a machine which could perform a task. And most importantly, humanoid robot is a machine which could interact with people. And is the last item, okay, which differentiate humanoid robot from industrial robot. And this slide shows you some example from this Honda company, and you will see, okay, we have an early version of a humanoid robot and the latest version of a humanoid robot. And this video will basically show you the capability of Honda's humanoid robot. So you see it's very much looks like a human being, right? And now I just share with you some of our research work in the domain of humanoid robotics. Okay, so in early 1990s, so we have developed the upper body of a humanoid robot. And also we have developed a very interesting technology, which is called as a single motor driven mud type independent joint. For example, for this prototype, and the arm itself has a 60-degree freedom, but inside we only have one motor. So one motor drive independently leaves a 60-degree of freedom. Okay, so this is a very interesting technology that has been developed by us. And in 1997, we have discovered this XI coordination principle. Okay, so basically it shows that the disparity inside the eye times a constant matrix will give us the displacement vector of a hand or two tips or head or body, whatever. Okay, so it's very generic principle for XI coordination. And we have a validate this principle with a robotic arm. So you see the picture, and then this has been broadcast in the national television program in Singapore. Okay, and 10 years later, this has been validated with a monkey. So you see the monkey's hand arm are restricted here. So we use monkey's eye to determine the theta X, theta Y, theta Z, and they use this signal to drive a mechanic arm. Then you will see the convergence in the vision guide coordination. Okay, so it's a very, very interesting research. So in early year 2000, I have published this book and established this journal. Okay, and this slide basically shows you some of our work that we have developed in early 2000. Okay? Okay, you see our prototype. And we also demonstrate this prototype to the public and in exhibition. And you see, okay, these are the picture taken from the exhibition. So our latest development is to miniaturize a humanoid robot. Then we have a handphone-sized humanoid robot. And this gentleman is a Minister of the Trade of the Industry in Singapore. So then we move on to the third part of my speech, okay? So I will quickly go through the 5 key steps which has been involved in the development of a humanoid robot. And this video will show you the latest achievement in biped walking in humanoid robot. Quite impressive, okay, demonstration. So I will, because I can spend an hour to talk about these key steps, okay? Since I have a limited time, therefore I structure all this content in these 5 areas, layer by layer. So it will help you to quickly understand, okay, the key step involved in the development of the humanoid robot. So let's start with step 1, which is about the hardware, okay? So humanoid robot bodies hardware, okay? And for the hardware, you will see the 3 keywords are appearance, structure, and the mechanism. So these are the pillar, okay, for this layer of development, okay? So you will see for appearance, we can, okay, work together with the artist, okay, in order to design, okay, the nice looking appearance, okay? And then from the design, then we can use a 3D printing technology to print out the appearance, etc. And the second pillar for hardware is, or mechanic system is a mechanism, okay, for the arm, body, leg, and the head. We may have a certain number of degree of freedom. So this picture shows you the layout of a degree of freedom, okay? And because of this degree of freedom, then the robot will be able to output the motion. Okay, so this is our prototype. So this is just a result testing. Okay. We show the slow motion so that you appreciate. Okay, so the different phase involved in the biped routine. Okay. We will step up and step down the same case. Okay, so I move on. Then for second key step is supply of energy. And for this layer, the two pillars are power supply and actuation. Because it's through the actuation on the mechanism, then the robot will provide the motion, okay? And inside the humanoid robot, which is very much looks like a mobile robot, therefore we must have an independent power supply inside the robot itself. And in particular, we must separate the supply of the power for actuation and the supply of the power for sensor or computing unit. This is why we need to have this type of a distributed power supply system, okay? Then for actuation, because it's through the actuation, the robot will provide the motion. And for humanoid robot, usually we have a higher number of degree of freedom. And here you see this is the loop. There's a sensor, actuator, and the controller. So you have a lot of a loop, okay? So therefore, so we must distribute the energy, okay, to each of these loop, because each of these loop will consume power in order to produce the motion, okay? So this is a second pillar for the energy flow, okay? And because of supply of energy, then robot can produce motion, okay? And the most complicated step is step 3, the signal flow, okay? Because there are a lot of signal involved, okay, inside the robot. And in particular, we have a signal which are related to motion, which are related to the force, torque, or energy. And here you will see, and the relationship among this signal will create these 3 pillars, okay, in this layer, the kinematics, dynamics, and the static. Okay, so we have the equation of kinematics, equation of dynamics, and the equation of statics, okay? So this is quite complicated in terms of mathematics, okay? So then if we follow the human being's blueprint, okay, for the design of a human being's body, then we understand our brain. Actually, we have a cerebrum and a cerebellum, okay? For cerebrum, we control the high-level activity, okay? It's like motion planning, task planning, behavior planning. Then for humanoid robot design, we can, okay, make use of similar blueprint, okay, to have 2 horse computer. One take care of a high-level planning and control, and another one take care of a low-level planning and control. Okay, so this slide shows, okay, this strategy which is inspired by human way of coordinating the relationship among the signal. Okay, then for cerebellum, so we can have a dedicated host computer to take care of the low-level planning and control of this signal or motion-related signal. Okay, then once we link these two together, then we will come out this complex control system inside the humanoid robot. And this control system will respond to signal, because at this level is a signal, at this level is a motion, okay? Then you will see we may have a behavior. So behavior will be translated into the motion. Motion will be translated into motion related signal, okay? And here is one example about this how to control the signal, okay, for the leg, okay. Just now you have seen this video. So this kind of feedback control to achieve control the signal level, okay. And also we can control the signal which come from the finger of a humanoid robot, okay. And also we can interact with the robot at the signal level, okay? But later on I will show you, we can also interact with the humanoid robot at the cognitive level or knowledge level, okay? So for this one, we just interact with the humanoid robot at signal level. For example, if we use a keyboard, actually the keyboard will emit signal. If we use a joystick, joystick actually emit the signal, okay? All right. Then the challenging part will be the equation which govern the relationship among all these signals. Okay, so for motion related signal, we have two types. One are the signal which are purely related to motion, and the second type are the signal which are related to energy, for example, the force and power. Okay, if we study the relationship among the pure signal of the motion, then we need to establish the equation of the kinematics. If we want to know the signal of a motion, relationship between signal of motion and the signal of energy, then we need to study the dynamics. Okay, then for kinematics, so you see the complexity, we must have a matrix of kinematic equation. Because for humanoid robot, okay, any one of them could be the base link, any one of them could be the last link. Therefore, from the base link to the last link, then we have a kinematic equation. So therefore, we must have this matrix of a kinematic equation, okay? And then this one just show you, if we have a single kinematic channel, then we have a well-established equation which will relate the motion of the last link with respect to the reference of the base link, all right? And then for dynamics, how to relate the motion to the force torque, okay? So then we have two situations. That means we apply the force torque to maintain a stable position. Therefore, we call it as a statics. Then we have a well-established equation. And in general, we must know, okay, how the force torque will contribute to the creation of acceleration. So then this is a universal equation which describes the relationship between force and torque and the acceleration, velocity, and the position, etc. Okay, and the challenge in humanoid robot will be the biped walking and the signal involved in biped walking. Okay. And in general, we also have three types of equation or model for the dynamics of a biped walking. The first one is inverted pendulum model. Okay, so we can write down the equation which relates the force to the angular acceleration and angular velocity. The second one is a cut table model. Okay, so we separate the upper body from the lower body. Then we can write down the equation which relate motion to the force torque. Okay, and the third one is an inverted arm model. That means we leverage on the knowledge for the arm manipulator. Then we treat the leg as an inverted arm. Okay, and then therefore then we can use arm manipulator's dynamic equation. Okay, so these are the three type of modeling for the study of humanoid robots dynamics in terms of biped walking. All right. And based on this knowledge, then we should be able to implement into the physical model. So these are the latest results from the Humanoid, Honda's humanoid model. Right, so continue. And once we have the signal flow, and when the signal vary in time, then the result will be the motion. And the motion is something related to the behavior and the task, okay? So it is an intermediate between behavior task and the low-level signal, because the low-level signal are needed for the automatic control, okay? Then motion is an intermediate description which bridges the gap between the task and control, okay? So for this layer, then the focus will be on these two pillars, planning and the control. Planning means to break down the behavior or task action into the motion description. Then control basically is to take all this plan, the signal as an input, then produce the actual signal as an output, okay? Then for the planning part, we may plan the grasping. In terms of grasping, then we have this typical action of open, close, move, stop, etc. Okay. Then once we break the behavior, so these are the behavior at the higher level. Then lower level are the controllable or desired signal to be produced by the humanoid robot. With this in mind, then we can supply this into the as an input to the feedback control loop. Then we should be able to produce an actual signal as an output. Okay. Then for manipulation at the high level, we may have this kinds of description, such as a push, pull, grasping, throw, follow, etc. Okay, and then this action could be the result of a task-based planning or intention-based planning or disturbances, okay, based planning, etc. Okay, and similarly, from desired task or desired behavior, then we have the desired signal. Then desired signal will be supplied to the input of the feedback control loop. Then feedback control loop will produce actual motion signal. Okay. So then at the control loop side, eventually we may mix up these loop together. So because at the inside at the lowest level of the feedback control, so these are the three typical type of control loop: position control loop, velocity control loop, and the torque control loop. And actually we can combine them together to have a hybrid control loop, okay, in order to produce the desired signal as output, okay. And for biped working, so you will see it is more complicated than manipulation and grasping, okay. So similarly, for each higher level of behavior for biped working, so then we must, okay, to plan the desired motion signal and supply this desired motion signal to the control loop, okay, at the low level in order to produce the actual motion signal, okay. So then this is quite complicated task. And this slide basically show you this achievement, planning and control. So with the planning control in place, then we are able to autonomously produce this type of behavior. Okay, so it's very impressive. Okay, so now we reach the last step, in which is involved in the development of a humanoid robot. So which is called as a knowledge flow. So this is the most challenging part in today's research in robotics and AI. And for knowledge flow, there are two pillars because vision and the speech are the two major source of information. Speech carry the knowledge, vision also, okay, transmit knowledge about the physical world. So these are the two major pillars, okay, inside the knowledge flow. But of course, so we may have other source of information which may also carry knowledge to the robot, okay? But these two are the major pillar or major source of knowledge, okay? So, and why this is important? Because today we can easily achieve a signal-based interaction between human being and the robot. And in future, what we intend to do is to achieve human-like, human-to-human interaction, because for human-to-human interaction, we heavily depends on the use of knowledge, okay? And which depends on our vision and our speech, okay? But in future, we want to achieve a similar behavior or scenario, okay? Let the robot to use vision and speech to interact with a human being, okay? But today, for vision-guided manipulation, there's no obstacle, okay? So we can easily achieve this kinds of, there's a hand-eye coordination, okay? But due to time constraint, I just quickly pass through. So today, robot can autonomously undertake hand-eye coordination is not an issue. And also to undertake vision-guided biped walking, okay? There's no obstacle, no limit. And also today, the knowledge about the biped walking is normal and obstacle because we have a good understanding of the way or the principle behind the biped walking, and okay, the space involved, the action involved, basic action involved in the biped walking, then how to combine the basic action of the leg involved in the motion to create the phase and make a transition from among these phases. So there is not the issue. Once we have this knowledge about the phase transition, then we can generate the behavior of the pelvis, for example, the upper body, etc. Then all the way down to the motion of the joint inside the leg, etc. And also we have a good knowledge about the biped walking stability in terms of a stability of a static walking, stability of a dynamic walking, etc. Okay, so the challenge here is, today's challenge in this area is the understanding or mastery of language, because in future we want to achieve this kinds of interaction between robot and the human being. Okay, so we have done some work like in this area. For example, this is the simulation. So let the robot to respond to the language. Okay, so you will see. So there's a dialogue, a conversational dialogue between the robot and so I just quickly play. Okay, so etc. You see the response, then we can eventually ask the robot what to search something, and the response what the robot have seen. Okay, inside the room, etc. Okay, so it's a language-based interaction, and this is a real test. Okay, so I can instruct the robot using English to take action. Okay, so I just quickly play. So that means in future we do not need to program the behavior of the robot. Just use the language to instruct the robot to undertake certain action. Okay. Then what will be the future work in order to make a breakthrough in the mastery of a human language, or in order to achieve robot intelligence? So this is in year 2009, we have advocated AI 3.1. Then 8 years later, DARPA in USA and the Chinese government also recognized that we have already reached the era of AI 3.0. And this slide shows you the blueprint of AI 3.1. Then you will see the human language is the foundation for us to achieve the third generation of AI, which will enable a robot to have its arm self-intelligence. Okay, then after AI, what will be the next research topics? So we believe should be the robot life or life like a robot, and this eventually may help us understand human life, what is human life, etc. Okay, so due to the time constraint, I just quickly share what we have done. Okay, so in summary, these are the key takeaways from today's speech. So by now, you should be able to understand why do we need to focus on humanoid robot research, and what is the definition of a humanoid robot. And in future, if you want to venture into this domain of research, what should be the key step for you to consider or for you to handle? Okay, so thank you for your attention.